All right, ladies and gentlemen, let's get started with reaction stoichiometry. Reaction stoichiometry is the exact same thing as compound stoichiometry, just with one extra step. In compound stoichiometry, you start with one substance and you just run through different units of the same substance. However, with reaction stoichiometry, this allows you to switch from one substance to the other with a reaction using the molar coefficients we get from the balanced chemical equation. Your equation must be balanced for these coefficients to be precise and accurate. The use of these coefficients is what we call a molar bridge. The molar bridge comes from the balanced chemical equations, but you have to be in moles to use the molar bridge. You have to be in moles to use the molar bridge. You have to be in moles to use the molar bridge. Don't go into the bridge until you've turned everything into moles. Because this molar bridge is the only place you'll use the molar coefficients. So for that process to work out accurately, you must be in moles. So when I say build a molar bridge, this is the layout I'm talking about. You have your given substance A, so that's given to you most times. That's given to you. And this substance B is the goal or what you're going to. So you can have whatever type of substance A, a mass value, a particle value, a volume unit, whatever, and you have the compound stoichiometry skills going in to turn it into moles of A. You can use, if it's a mass value, you're talking about that molar mass. If it's particles, formula units, molecules, atoms, anything that means part of a whole, we're going to use that Avogadro's number. And if it's a volume situation, we're using the 22.4 liters to get us into moles of A. Right here is where we start to build a bridge. This whole part right here, especially right here, is where we're starting to convert from substance A into substance B. This is where we start to use your molar bridge and your molar ratios found from your coefficients from your balanced chemical equation. This part allows us to turn from A into B. Notice how moles of A is here and moles of A is at the bottom because we're trying to get that to cancel. We're trying to get that to cancel, leaving us in moles of B to then use compound stoichiometry to get us into whatever the problem's asking us for, whether it's a mass value, particles, or volume unit. So it's compound stoich going in, a momentary use of reaction stoich, and then compound stoich going out. So they're a combination of skills. And these molar ratios come from those coefficients in your balanced chemical equation. So make sure we understand that what goes in here is balanced chemical equation coefficients. So it'll be your co-F of B and co-F of A. So here's one that's already been pre-worked for you. So first step, you always convert to moles. I can't stress that enough to you. Unless the moles are given to you, take the blessing and move on. And then for your second step, you convert A to B using that molar bridge. So in this example I've pre-worked for you, we're talking about how many liters of CO2 are produced if 75 liters of carbon monoxide is burned in the presence of oxygen. So I have a given substance A and a goal of substance B. Your question here, how many liters of carbon dioxide? That's a key indicator so you know it's substance B. Substance A is what's given to you. So then we go forth and prosper with your balanced chemical equations. This part will be given to you or you'll be asked to produce it. Remember your diatoms and remember how to balance. Remember how to balance. So we got to make sure we're balanced here. So I see this 2 going to carbon and oxygen. That diatomic oxygen making 4 oxygens on the reactant side. This 2 coefficient going to that carbon and to that oxygen. 2 times 2 is 4. 2 times 1 is 2. Then I got 2 carbons over here. I'm balanced. Or go through the inventory process if you can't do it in your head, and you get started. For this first step right here, this is your given information from substance A. This part is given to you. That's in liters. I need it to be in moles for me to start my bridge. So I turn into moles of substance A using that 22.4 liters of carbon monoxide. Now those liters cancel. I'm sitting in moles of substance A. Now I start to build my molar bridge. To my molar bridge comes from my coefficients from here. So I start with moles of carbon monoxide at the bottom, so I'm trying to get that to go away. Then I put my goal up top. I'm trying to get to liters of CO2. So first, before I get to liters, I got to get to moles of CO2. So then in my balanced chemical equation here, I see my CO I got to get to cancel has a 2 coefficient. I write that there. And then my CO2 has a 2 coefficient. I write that there. And I keep going. Moles of CO cancel. Now I'm sitting in moles of CO2. That's cool. That's great. That's not what I'm asked for. I'm asked for how many liters. So then I use my 22.4 liters of carbon dioxide to move from moles to liters, canceling out my moles, giving me my answer. So I take my whole top by whole bottom, I divide the two. So I'm doing 75 times 1 times 2 times 22.4, getting me a number. Then I take 22.4 times 2 times 1 to get a number. I've done that for you here. You divide the 2 and you get that number. Accurate to 2 significant figures gives you 75 liters of CO2. Remember, your answer format is always number, unit, substance. Always. That's your answer format. Number, unit, substance. So now here we go. Let's try another one. If 3.4 atoms of H2 are produced by decomposing water, how many molecules of O2 are produced? I'm talking about H2 gas here. So you should end up with 1.7 times 10 to the 23rd if all the math is mathin'. So let's see. You take what you're given and run with it. You take what you're given and run with it. Let's validate this answer. I have a starting place. That's here. I've already pre-balanced my equation, so I'm good to go. I would 10 out of 10 recommend putting number, unit, substance within your conversion factors here, so that way things don't get messy. You want to know what you're in and where you're going. So I'm currently in atoms of H2. So if I'm in atoms of H2 to get to moles, I gotta get those atoms to go bye-bye. So in 1 mole of hydrogen gas, I have 6.02 times 10 to the 23rd atoms of H2. Now, very nice and neatly does atoms of H2 cancel, leaving me in my moles. Now I'm good to start building my molar bridge. I build my molar bridge. I'm trying to get to how many molecules of oxygen are produced. I'm trying to get here, molecules of O2. So I should probably move into moles of O2 up top. And I gotta get my moles of hydrogen, or H2, to cancel, so hydrogen goes on the bottom. Now I'm using that molar coefficient we get when we balance here to start filling in my molar bridge. I have a imaginary 1 in front of that oxygen, and in front of my H2, I have that 2 here. So far, I'm sitting now, I've done my molar bridge, because that's what this part right here is, a molar bridge. Now I'm sitting in moles of oxygen. That's not what I'm asked for. I'm asked for molecules of oxygen. So I keep going. I know for every 1 mole of O2, there are 6.02 times 10 to the 23rd atoms, or molecules, excuse me. Boop, boop. Let me get my eraser. Molecules of oxygen. I'm in what I need. Now I just do some math. Let me get my calculator handy dandy here. No. All right. Whole top over whole bottom. Remember, anytime you see scientific notation, keep scientific notation in parentheses always. You're trying to do math with that whole number, not just parts and pieces of it. So if you don't put it in parentheses correctly, you won't get the actual value you need. There we go. Struggling here for a little bit. Times that 1, times that 1. That doesn't really do anything for us. However, that 6.02 times 10 to the 23rd does. And there we have it. We'll have a whole top. Now, I should never see e's in your answer. We are better than that. E means times 10. And then you do the whole bottom. Six 6.02 times 10 to the 23rd times 2 times 1. So then I'm going to open my parentheses, recall that one down. Notice how I keep it in parentheses. 1.7 times 10 to the 23rd. Number, unit, substance. And if memory serves, that's my answer I was given. So my answer has been validated. That's the process we're going through. So you just got to read your formula here and determine what is substance A and substance B from your given equation or your given problem. So I'm given 33.4 atoms of hydrogen. That sounds like substance A. Then we're going to slither over here to how many, that's my question, molecules of O2 here. So that, friends, is substance B. So I move from A to B through that reaction stoichiometry, and we call it even. Carrying on, let's do another one. All right, so if 5.0 grams of potassium chloride are decomposed, how many molecules of oxygen are produced? So I'm given 5.0 grams of potassium chloride. So would that be substance A or substance B? That's substance A. And over here, you're asked to decompose to how many molecules of oxygen? How many molecules of oxygen? That is substance B. Now, this equation's not balanced because, one, I know better. Oxygen is diatomic. So let's get to work here. I'm going to do it long ways just for continuity's sake. Okay, C. Oh, not C. Oh, Jesus. No. There we go. Cl. O. Same order on both sides, always. You don't have molar masses for polyatomics as a whole, so better bet is to bust them up into the parts and pieces. So that way you can get an accurate count. I see 1 potassium, 1 chlorine, and 3 oxygens. On my product side over here, I have 1 potassium, 1 chlorine, and 2 oxygens. I need to make that match. This is an even odd conflict I see here. So my least common multiple would be 6. So I'm looking for something times 3 and something times 2 to get me to 6. I know 3 times 2 is 6. So I'm going to throw a 2 over here and a 3 over here to run that through, and then I'm going to reevaluate my inventory here. So that 2 times that 1 is a 2. That gives me 2 CLs as well, but 2 times that 3 on oxygen equals 6. So, okay, let's see how we're working over here. I probably need to put a 2 right here to make everything balance out. So do. Yeah. And that leads me to 6. And it looks like everything is balanced, and I can't simplify it because 2 can't go into 3. So I'm good to go. I now have a balanced chemical equation here, and that's bothering my OCD a little bit. So we're going to erase that. So that way it's nice and easy to look at. Now, I have a balanced chemical equation. Go to work. Start with your given. You are given 5.0 grams of KClO3. So I need to move into how many molecules of oxygen. So this is substance A. I'm in grams at the moment, so I need, for every 1 mole of KClO3, I'm going to use that molar mass of KClO3. To start making things move a little easier. Grab my reference sheet over here. You would think by now I would have these all memorized. I'm good. I'm not that good. All right. Multiply across, add down. So we're going to slither that calculator back. I'm going to do it all at one time here to save some time on the video. I don't know why that has so many extra parentheses. Okay. 122.55. Sitting in moles of A, now I can build my bridge. I'm asked for moles of oxygen coming from moles KClO3. Now I'm sitting in moles of B, but I'm asked for molecules of B. So same thing here, we're going to introduce that Avogadro's number. over 1 mole of that. Well, that's not my final answer, though, because that is far too many numbers. I'm giving 2 sig figs here. So I'm going to move this down to 2 sig figs. And boom, bow, just like that, we're done. So far, pretty straightforward process. You just start with your given here, and you move into moles of given. Build that molar bridge right there to give you your key to success. This right here is a molar bridge. It's leveraging that molecular molar ratio to turn from substance A on this side to substance B over here. To substance B over there. You can't see that at all. Do. There we go. Better, so where y'all can see. And this is just compound Stoke over here. And this is the reaction Stoke process. Integrating this molar bridge is reaction stoichiometry. So it's compound Stoke going in, manipulate reaction stoichiometry, and compound Stoke going out. That's how you tackle these. So let's do another one together. So I asked for if 54.3 liters of carbon dioxide are produced in the following reaction, what volumes of carbon dioxide and O2 are required? So what volumes of carbon monoxide and carbon dioxide are required? If it's asking for volumes, plural, you got to do them both. So, okay. Start with your given. That is substance A. And I'm asked to move to what volumes of CO and O2 as substance B. So you just treat them independently. So let's go to carbon monoxide first. Why not? Turning that CO2 into moles with 22.4 liters of CO2. Now I'm going to build my molar bridge here. So I'm going to moles of CO to moles of, from moles of carbon monoxide, but I've done a fundamental skip here. And hopefully you're in your chair hopping up and down telling me so, because this is an unbalanced mess. So I should see a 2 right here after you're done balancing, a 2 right there, and another 2 right there, just to make things nice and even. Then we continue with our molar ratios. So now that I'm pleasantly sitting in moles of carbon monoxide, I start moving into what I'm asked for as to volume of carbon monoxide. So now I gotta go into trying to get that mole to cancel. So now I need 22.4 liters of CO. And then we're gonna do the same process down here. I'm gonna get my setups and then I'm gonna just do math all at once. So we're coming from the same spot, 54.3 liters of CO2 times 1 mole of CO2 over 24.4 liters of CO2. That gets me from liters of A. Now I need to get into moles of A so I can then slide into my molar bridge, coming from moles of carbon dioxide to moles of oxygen gas. And that, ladies and gents, is a 2-to-1 ratio right there. But that's moles of oxygen. I'm asked for volume up here. I'm asked for volume of each. So I add in another one, 22.4 liters of O2 over 1 mole of O2. Then we just sit down and do some math. All right, y'all, so let's do some math here. We're going to take 54.3 times that 1 times 1 times 22.4. Get a whole top value here, 22.4 times 2 times 1, of course. Whole top over whole bottom gives me a whopping 3 sig figs here, excuse me. Liters of O2. Do the same thing. Over here for up top, 54.3 times 1 times 2 times 22.4 divided by 22.4 times 2 times that 1's not going to help us much. 3 sig figs. 3 sig figs. And look, Mom, we can do it. Easy, breezy, beautiful. Cover girl. So hopefully these are starting to get a little more intuitive for you. Now I'll give you a second to start this one. I encourage you to pause the video and try it on your own to make sure your skills are up to par, muster, or whatever you want to say about, so you know what you're doing. But I'm gonna go ahead and get started. Because I can see that I'm given atoms of H2 are produced. That sounds like a substance A. Then I'm moving into how many molecules of O2. That sounds exclusively like a substance B. So then we go to work. Atoms of H2. All right, atoms of H2 need to be in 1 mole of H2, so that would be divided by 6.02 times 10 to the 23rd for Avogadro's number. Now I'm in moles of A, so now I can start building that molar bridge. Oh, no, I don't want a crayon. There we go. Trying to get that mole of H2 to cancel to move into moles of O2. But hopefully we're still screaming up and down in our seats because I haven't shown you a step that's very, very, very important to make sure your right ratio happens. Because without this right ratio, everything you're going to do goes left. So before you sit here and do all of this good work, let's make sure our equations are balanced. Let's make sure those equations are balanced. Comes from O2, that's a 1. H2, that's a 2. That's going to bother my OCD a little bit, so we're just going to fix that right quick. Now I'm sitting in moles of O2. That's not what I was asked. I was asked to give molecules of O2, so for every 1 mole of O2, I have 6.02 times 10 to the 23rd molecules of O2. And go ahead, in your work, I want you to put a box around the molar bridge. Put a box around where you see yourself moving from substance A to substance B. That, ladies and gentlemen, is your molar bridge. That's the really important step that allows us to move from one substance to the next. So then we're going to slide our little calculator back into the equation here and keep all that scientific notation in parentheses. Keep it in parentheses, because otherwise life gonna go get messy. And we don't want messy, we want easy, breezy, beautiful cover girl. Whole top, whole bottom. And hopefully by now we are clear on what I mean by whole top and whole bottom. So I'm going to open up parentheses and recall down that top value. Divide that by, 2. All right. Ta-da! And that's just the validation of this one up here. I encourage you all to try this next one on your own. Pause the video and try it on your own to make sure your skills are where they need to be and we get the same answer. But let's get into it. So first things first, you should be jumping up and down in your seats by now to tell me to balance this chemical equation, because oxygen's a diatom, so I know I need that. Now that's not the same. And through the power of pre-work, we know that that's the balance. So if you go through and balance the chemical equation and don't get that, retry. You should see an even odd conflict you have to fix. So here we go. I'm given the gift of an original substance are produced if 25 grams of potassium chloride reacts with oxygen. So that, my friends, is a substance A. And I'm asked for how many grams of potassium chlorate are there. That, friends, is a substance B. So let's go to work. I'm starting out with 25 grams of KCl. If I see grammage, I can go ahead and assume I'm gonna need a molar mass here shortly. So, do a molar mass. hopefully we can get there and get the same answer here. So you can do it all at the same time in a calculator if you want to. Save yourself time and develop those calculator skills. However, if you are not confident in your calculator skills, don't do this. Do it very stepwise like I taught you. Multiply across, get those numbers, add down. Now I'm sitting here in moles of substance A. Moles of substance A. I'm going to slide my way back to my molar bridge part. My molar bridge is designed to get me out of KCl and into what I'm asked for of KClO3. So I'm using my molar ratios I have from my balanced chemical equation here. So that 2 goes up there and that 2 goes right there. Now I'm sitting in moles of substance B. I need to move this shenanigans down a little bit before I start running into some problems. Now, I'm in moles of KClO3. I'm asked for grams of KClO3. So I use my molar mass skills to develop a molar mass. Now I'm in, for every 1 mole of KClO3, I have 122.55 grams of KClO3. And just so we can see how that goes in the calculator, I'm going to put it in all at once again. If you are not confident in your use of parentheses or how to manipulate a calculator, you don't have to do this step. You can do it very stepwise like I've taught you. Now we do whole top, whole bottom. (25 times 1 times 2 times 122.55). Get that number, and 74.55 times 2. Get that number. Whole top over whole bottom. Divide the 2. Divide the 2, and here we are. 41.0965794,769 grams of KClO3. That is not your final answer, however, ladies and gentlemen. That has far too many numbers. We are given a whopping 2 sig figs to work with here. So we should report our answer and the appropriate number of significant figures. That rounds up to 41 grams of KClO3. All right, so that is the overview of reaction stoichiometry. I hope this is helpful for you to help see how it happens. And that's the basis of how to go from one substance to the next. I'll see you in the next one.